Video 2 for magnetism. Let's take a look at the concept of induction. So here, there's something called the left-hand rule, and if we look at this, what the left-hand rule does is it tells us how we determine the direction of force that's created by current running through a wire. So when you take current and you put it through a wire, there's an electric field, a magnetic field that is induced in the wire, and that magnetic field has direction. It has a direction of line of force. And if we look at this drawing here, we can see, so left hand, we put our thumb in the direction of current flow, and our fingers, as they wrap around here like this, as they wrap around like that, that denotes the direction of that induced field. So if I was to draw like that, I would have a direction of induced magnetic field in that direction like that. So my fingers here wrap around the wire, my thumb pointing in the direction that current's flowing. So current is going, so I have a negative here and a positive here. We're going to say current's going in this direction here. And so I put my thumb in that direction, in line with that. Then my fingers wrap around, and that denotes the direction of the induced magnetic field. Now, if we take a look at this conductor and we look at it from this end here, so we're going to turn it towards us, so we're looking at it from the end here like this. And if we're looking at it from the end, we know that we're going from negative to positive, so that current is actually going away from us. So if we're looking at it, it's going away from us. So what I like to do is draw an X in there to denote that it's going away from us. And you can think of that as an arrow. So if you shoot an arrow, that's the tail feathers of that arrow. So I got an arrow like this, and I've got tail feathers coming out the back. So it sort of looks like an X over here. And then if I was to look at it coming towards me, really all I would see is the point of the arrow, this one here. So this denotes that it's coming towards me. This denotes that the current is going away from me. So if I use this same principle where I put my thumb in the direction that this is going, I place my thumb, I point my thumb towards it, my fingers will wrap around in this direction. So that is the induced magnetic field as a result of the current moving through that. Now if we look at this one over here, so using again my left hand, I'm going to position my thumb going towards me, just like the arrow, the point of the arrow is coming towards me, and my fingers wrap around this in this direction here. So we can see that the direction of the current flowing through the conductor is directly related to the direction of the magnetic field that is induced around that conductor. So again, as it says here, the thumb points in the direction of current flow. The fingers wrap around the conductor in the direction of the induced magnetic field. So I've got 6 here we'll do together. And if we look at this, I'm going to say, okay, I've got current going away from us, current coming towards us. So let's do this first one here. So if I'm going to have current going away from us, I'm going to place my thumb into the page, and my direction of magnetic field is in this direction here. And if I have my thumb coming towards me, just like the point of the arrow coming towards me, then I'm going to have a direction of force around this wire in this direction here. So if we do the same thing with this one here, so I'm just going to change this. I'm going to change this to here, and I'm going to change this to going away from us, so coming towards us and going away from us. Now if we look at this one here, well, this direction, I know I'm going to place my thumb in that direction. That's going that way, and this one here is going that way. So if we look at the direction of force here, you know, we've got this going this way, this going this way. So we've got flux, if we think of flux, and flux lines don't cross, we've got these flux lines, they're both going in the same direction. There's going to be a repulsion there, because on a magnet, if I have these flux lines are coming out and they're going like this, and they don't cross. You see? They don't cross, and they repel each other. And because they repel each other, there's tension in those lines. So if there's tension in the lines, we have this repulsive effect. And then if we look at the first one that we did here, we have very much the same thing. We have very much the same thing. We've got the force here like this and the force here like this. So we have a repulsion there. So let's do this last one here. And I'm going to say, okay, well, I've got the direction of current coming towards me, direction of current coming towards me. My thumb is going to go out of the page towards me, so my direction of magnetic field is this way. And then same for this one here. Now notice the difference here in that these are going in the same direction. So if I was to look at this one here and this one here, these flux lines are actually in the opposite direction. So there's going to be an attraction here between these two. And what ends up happening is something called magnetic coupling. And what ends up happening is that these flux lines will couple together like this. And then as a result, you end up getting a stronger magnetic coupling effect here versus over here where we've got repulsion. So again, these are drawings, these are looking at the wires from the ends, so you can make a determination as to the direction of that induced magnetic force. Now let's take a look at the left-hand rule to determine the polarity of electromagnets. So what I'm going to do is I'm going to draw in some wires here. I'm going to say, I'm going to draw on this one here. So I got a wire that's being wrapped around this metal, and it's a soft iron core, very permeable, with a very low reluctance. And I'm going to say that my direction of current, so is like this. I got a negative there and a positive there. So my direction of current, it's going in the negative here, like this. And it goes in behind there and then back up like this. So my direction of current is like this. So it's going in here and it's going out here. So we use the left-hand rule again. And what we do for electromagnets is you take your fingers and you wrap them around that coil like that. So you can laugh at my hand drawing, that's fine. So I've got my coil here like this, and what I'm doing is I'm taking my fingers and I'm wrapping it around that like that. You know, I got the wire going up through there in that direction. So when I look at this, I say, okay, well, the current's going in this direction, and I've taken my fingers and I've wrapped my fingers around this coil in this direction here. And what's going to end up happening is my thumb here, my thumb is going to point to the north polarity pole of that electromagnet, and of course that'll be my south pole over there. So let's try another one here. What I'm going to do is I'm going to change something here. I'm going to say, okay, my wire is wrapped around like this. I'm going behind it first and then out like that. So my wire is wrapping around in this direction. And we're going to say that I have a negative here and a positive there. So really all I've done is I've just changed the direction with which that wire is moving around that piece of metal. So my direction, my current goes like this. It's moving in this direction. And then, of course, if I wrap my hands around, I'm going to be going in behind it. I'm going to go in behind it and down. So my hand's actually coming from in behind this and then down in this direction. So my thumb in this case is pointing to the north and south there. Now if we do our one more and I take a look, I go, okay, well, I got a wire like this. And I'll put the positive here and the negative here. My direction of current is flowing this way here, and if I wrap my hands around this again, then I'm going to end up having a north and a south here. So the direction of current plus the direction of the way it's rotated around.